So in the last video we talked about finding out inverses of element. Okay. So we took this example that you have 2 by 3 and you need to report p times q inverse in the answer. So you're getting 2 by 3 as answer and you need to find modulo 10 to the power 9 plus 7. So you find out 3 inverse, and for 3 inverse you will need 3 to the power whatever the prime p is, p minus 2 modulo the prime, right? Now this is a pretty large number, right? This is a very large number. So how do you find out this number fast? 3 to the power this number. This is not really trivial, right? If you loop directly, that's not a solution, because then you will have to loop up to 10 to the power 9 plus 7, and that's of order complexity 10 to the power 9, and that won't pass time limits in any of the problems. So how do we calculate this fast? So let's directly go to the general version of this problem. So we would be needing to calculate a to the power b sum modulo c. Okay, we need to calculate a to the power b sum modulo c. How do we calculate this fast? So one obvious way would be an order b solution. What is an order b solution in this case? What is an order b solution? Just loop over the numbers, right? Just loop over, like you just loop b number of times, like answer multiplied by equal to a, do it b times, you get the answer in the variable answer, right? So that is an order b solution, but that's not sufficient in most of the cases because the primes are large. So how do you still find a to the power b? So for this we use a technique called binary exponentiation that we'll be discussing now. Okay. So what is this binary exponential that I'm talking about? Okay. So we need to do it better than order b. So let's say we had to calculate this only for values of the form 2 to the power k in the b area. So let's say you had to calculate 2 to the power 3. Okay, how can we do this computation? You have 1, you multiply it with 2, so you get 2. If you square this, you get 2 squared, right? If you square this, you get 2 to the power 2 to the power 2, right? If you square this again, you get 2 to the power 2 to the power 3, right? So this is the starting point, this is the first number, and if you keep on squaring them up, you start to increase this power over here, right? Because that's where the multiplication is going up. So if you have a number 2 to the power k, if you square this up, you get 2 to the power k times 2 to the power k, that is 2 to the power 2k, right? So this power over here is increasing, right? Every time you square, the power is getting multiplied by 2. So how can we use this to our advantage? How can we use this to our advantage? Let's look at that. Let's say you need to calculate, let's take some big number now. Let's try to calculate 5 to the power 117 modulo 19. Okay, let's try to calculate this value. This is really large, right? And this modulo is not on the numerator, it's rather like you need to calculate the answer, this power, after taking everything modulo 90. Okay, that's what we want to calculate. So now the idea that we'll be using is write this thing 117 in binary. How do you write 117 in binary? So for this you can write it in binary in this way at 1, right? This is how you write 117 in binary. Yeah, that's correct. So this is 117 in binary. Okay, now this is nothing but 5 to the power 2 to the power 0 plus 2 to the power 2 plus 2 to the power 4 plus 2 to the power 5 plus 2 to the power 6, right? So this is the binary number, right? So if you write it in expanded it in binary form, this is the number that represents 117. So we are expanding the 117 in the binary form in the numerator itself. Okay, now we can distribute this plus as multiplication in the base, right? So this would nothing be 2 to the power 0 multiplied by 5 into 2 to the power 2 multiplied by 5 times 2 to the power 4 multiplied by 5 to the power 2 to the power 5 multiplied by 5 2 to the power 6, right? This is how you can write this, because when the base is same, you get addition in the powers. So when opening it up, you go the reverse way, right? Now notice something that this is nothing but 5 to the power 1, right? This is 5 to the power 1. This is 5 to the power 4. This is 5 to the power, these numbers, like what you're multiplying, 5 to the power 16, 5 to the power 32, 5 to the power 64, right? So we need these numbers to calculate this value, right? If we can find out these numbers, we can multiply it and get this value. So how do we find out these numbers? Pretty fast. So suppose we know 5 to the power 1. We can square it to get 5 square, right? We can again square this to get 5 to the power 4. We can again square this to get 5 to the power 8. You can again square this to get 5 to the power 16. We can again square this to get 5 to the power 32, right? So on. Now you see, when we are squaring this up, we are getting these values like 5 to the power 1, 5 to the power 4, 5 to the power 16, 5 to the 32. That will be used in this computation, right? These are the values that are getting used in this computation, because we have broken down these in binary form, right? So only 2 to the power k form will be present in over here, and if we keep on squaring, we will get all these 2 to the power k forms that are possible. So during these calculation or expansion, we will get all these 2 to the power k forms, and we can, whenever we get that value, we know that we need these value, we plug in that value into this expression. Okay, so we find out these values. Whenever that becomes relevant, we put it in the correct place, and we see that okay, we need 16. We keep on keep on going up. We see okay, we know 5 to the power 16. We plug in the value over here. 32 plug in over here. Sorry, this goes up to this part. After this, you will get 5 to the power 64 that you can plug in over here. So all of these values are sure to be appearing in these expansion sequence that you have, right? So this is the property that we are going to exploit while finding the binary exponentiation, that we have these 2 to the power k forms and only these forms appear, and if you can somehow save all these values, or even not without saving, you can compute them on the way such that whenever it comes up, you just put in the value in the expression. So one simple idea would be to just keep a mark on, like you need 0, 2, 4, 5, 6 and start jumping in squaring ways, so you know which values you are getting into. Like when you square, you are first at 0, then you go to 1, then you go to 2, like this is how you are squaring, right? So when you square, you know that from 2 to the power 2 to the power k, you go to 2 to the power 2 to the power k plus 1, right? So this is how you are squaring. So you know you are keeping on increasing over here, 4, 5, 6, so on, right? You are increasing over here, and whenever you see whenever you see that you have a correct value, you just place in that value. Like you have this value 5 to the power 2 to the power 2, and you know that need 2, so you just plug in this value and then wait for this value and then keep on going up, and you see that okay, you have 4, plug in that over here, keep on going up, right, until you see the last one. Okay, this can be a direct idea that you can use. Now why are we doing so much of complex thing over here? Okay, why are we doing this? So if you pay some attention to this, how many terms can be there? What is the, let me ask it in this way, what is the 5 to the power 2 to the power some k, okay, some k, what is the largest k value that it can take, that you will need for any particular b? So suppose you are calculating a to the power b mod c. Okay, now what is the largest 5 sorry, this would not be 5 anymore, this would be a. Okay, okay, so what is the largest a to the power 2 to the power k, 2 to the power k, okay, you're gonna need in this computation? That is the largest, the largest power of 2 in this b would be the value of k, right? Like you will write this in 2 to the power 0 plus 2 to the power 1 so on up to 2 to the power k, right? Some 2 to the power k, and that k would be the last to a to the power 2 to the power k that you need, right? Because that's where this a will get distributed. So if you divide this b in binary, the k that comes up last is the one that you up to which you will need to go. Now if the value is b, what is the maximum k it can take? So 2 to the power k is less than equal to b, right? So k is less than equal to log 2b, right? So you will only need to go up to a k value which is log of b, okay? And in every step your k is increasing by 1, because in every step of this squaring, we know that if we square a number of the form 2 to the power 2 to the power x, it goes to 2 to the power 2 to the power x plus 1. So every step you are increasing by 1 and you only need to go up to log of b. So your computation over here will take log of b method, b time or number of steps, okay? So now with this kind of idea you can calculate a to the power b mod c in an iterative fashion in log of b time, order log of b, okay? So now for implementing this, when you have these 0 2 4 6, you don't know which these values are, right? So what we can do is that we can somehow maintain these binary forms, right? Like there is a binary form from this, right? Binary form for a number. So we can somehow maintain these binary form of numbers, and okay, and this one at end means that okay, you need this value. So let's suppose you have a, okay, a to the power 2 to the power 0, that is a to the power 1, okay? So that this 1 over here means that you need this value, okay? So there is an answer, you multiply it with a to the power 2 to the power 0, okay? Then you square this, so that gets to a 2 to the power 1, okay? And you divide this number by 2. So what happens when you divide a binary number by 2? Like there is a binary number, let's suppose there is a random binary number. When you divide it by 2, the last bit gets stripped off. That's what happens. And by 2, I mean to say it's an integer division, so even if it's odd number, that gets removed. So whenever you have a binary number and you divide it by 2, the last number gets off. So you remove that and this is your new number. So you just divide the b by 2, okay? So this is your new number and you have increased your a. So now after this part you see this is 0, so you don't multiply this and you square this again. So you go to 2 to the power 2 to the power 2 and you again divide it by 2, so you remove this. Then you see this is 1, okay? Then you need this value, so you multiply it with this and then you again square this number, and we know that when we square we go to 2 to the power 2 to the power 3, you divide it by 2, then you see you don't need this, then you go to the next number, you divide it by 2, you multiply it with, you square it, sorry, this would not be k, this would be 4, right? Now this is 1. Now when you divide all of, when you have removed all of this, this is 1, so you will need this number, so you multiply that and you divide this number and then you multiply this to the power 5, right? And then you see you need this number as well, so this will be 2 to the power 5. Then you go to a 2 to the power 6, you remove this bit as well, then you need this as well because this is 1, and then a into 2 to the power 6, then you remove this as well, and then you see that this numbers become 0. Like once you divide, like when you have 1 and you divide it by 2 by using a floor division, okay, then it becomes 0, right? Like 1 divided by 2 is equal to 0, like in floor division, right? So once this becomes 0, whatever you have multiplied is the answer. Now you were squaring things up, right? You were squaring things up. Whenever you square, make sure that you take modulo properly, because if you take a multiplied by a, you need to take a modulo, right? So whenever you're taking modulo, make sure that you first modulo these and these, and then you multiply these two numbers, right? Also, when you are multiplying these answers over here, like whichever last bit was 1, you had to multiply this with this, right? With the answer, we have to multiply that in the answer. So whenever you are multiplying that thing in the answer, you need to take a modulo as well. So if you carefully do these modulo operations, you'd be able to find out any a to the power b mod p in log of p time, right? In order log of p. So this is the order log n algorithm to calculate a to the power n. And since most of the cases a to the power n happens when n is large, or even if a is large, you can still calculate things in mod p, right? That's what the benefit of mod is. So even if n is large, you just need log n number of steps, right? Even if a is large, you can first of all put in the mod p inside the a, and then make it smaller, and then find the power using the same algorithm. Okay. One thing that's mentioning is that you can use this exponentiation technique. This is called binary exponentiation. Even if you had to calculate 0 to the power 95 to the power, let's suppose 100. Okay, even if this a was some floating point, you could have used this algorithm. Why? Because you just need to square things up, right? You can square float numbers, okay, and you just need to keep on dividing the p by 2. That you can do with this integer, right? So as long as the power is prime, this base a can be anything. It need not be a number. So we were dealing with numbers modulo p, but it can be a floating point as well. In fact, just an idea, it can even be a matrix. Like if you had like a simple matrix like this, and you had to calculate to the power 100, you can use this exponentiation idea to calculate this faster than multiplying it 100 times. Okay, so this is the idea of binary exponentiation. See you in the next video.